Recall that to find the global min or max of a function of two input variables, we should find the critical points of the function. And the usual scenario for this is when are both partial derivatives equal to 0. Less usual is when at least one of the partial derivatives does not exist. Okay, so you get these critical points, then we have to classify them. So compute second partial derivatives so that you can compute the discriminant, which will be f sub x times f sub y minus the quantity f sub xy squared. So that's almost always the case anyway, because the functions we tend to be examining are going to be continuous. So then at each critical point, to figure out what kind of critical point we have, if you compute the value of this discriminant to be positive, then you're going to have a local extreme. And then we ask what kind of local extreme? Well, if f sub xx at that point AB is negative, then f has a local max. If f sub xx is positive, then f has a local min. If the discriminant at that point is negative instead of positive, then f has a saddle point, and then if the discriminant is 0, then you get no information. Now we're going to add one new feature on top of that, which is sometimes you're given a region R, and you might be asked not to minimize or maximize your function f just anywhere, but you might only want values xy that fit inside a certain shape. So if that occurs, we're going to skip any critical points that occur outside of R. And the key thing is to check the boundary. So this is a lot like in Calc 1 when you're given a function y equals f of x and you're asked to find the min or max, but you're also told that x should only be between, I don't know, 2 and 8, then you still have to check the boundary. What happens at x equals 2 and what happens at x equals 8? Okay, so just a little more detail about checking the boundary here. There are a lot of tasks that are like Calc 1, so to find the global max, okay, same story for global min, but let's just talk about global max. Find all local maxes in the interior of the region using the second derivative test, and then compute local maxes on the boundary. This is just like checking endpoints. Look through the list that you get to see which input, xy, is going to give the largest output, z. And yeah, as was already kind of previewed a moment ago, finding the global max in Calc 1, for x belonging in 4 to 9, you'd have to check what's the y value when x equals 4 and what's the y value when x equals 9. Right? So for an interval, like in Calc 1, the boundary is just the two endpoints. Now the boundary is a little more complicated. So for a function z equals f of x comma y, a Calc 3 style function, R is usually a filled in two-dimensional figure, something like a triangle or a rectangle, and the boundary is the perimeter.